Okay, today's video we're going to be talking about Ethernet. What is Ethernet? I mean, it's not just Ethernet cabling or Ethernet frame. It can be thought of like a family of standards. Those standards are issued and maintained by the IEEE. So with Ethernet, let's start at layer one. Layer one for Ethernet, you're going to have items like a hub. This would be layer one. So within that hub, you have Ethernet cables that connect everything together. I went ahead and wrote down some of the most common ones you'll see today, which would be fast Ethernet and gigabit Ethernet. But back in the day, popular was Ethernet. It was a 10-base T. The T stood for, it was a UTP or STP type of cabling, twisted pair. You could get 10 megabits of speed and up to 100 meters. Fast Ethernet came out and you could get 100 meters or 100 megabits per second. The new popular is gigabit Ethernet, which you get 1,000 megabits per second and up to 1,000, or it's still 100 meters for the copper. I wrote down some fiber optic specs here. 1,000 base LX can get 5 kilometers and SX can get 550. But before hubs came around, they simply just used a bus. And what a bus did, it allows companies to interconnect PCs. And what a bus is, it's a coax cable. Everybody shared the same line. So if PC2 went to send a frame to PC1 or a data packet, and PC1 was trying to send a data packet to PC2 at the same time, there would be a collision. So hubs were invented to lower the chances of getting collision, but it didn't prevent it. To prevent hubs, or to prevent collisions, they came up with something called carrier sense multiple axis with collision detection. And it's a way to recover from errors. And so if we take this right here and we'll throw in a hub. So how carrier sense multiple axis with collision detection works, if PC1 is sending a frame or a packet to PC2, and PC2 sends at the same time and there's a collision, both PCs will back off and they'll wait for an undetermined amount, and I apologize, let me start the carrier sense, how it actually works. Before a PC sends a frame, it's going to listen to the line first, and if it doesn't hear any communication or chatter, it's going to send its frame. After it sends its frame, it listens for a collision. If it hears a collision, it will back off and wait an undetermined amount of time, and then it will listen again and then resend the packet, and hopefully there will be no collision. So that's how it recovers from a collision. That's pretty much layer one. Layer one is pretty simple. It deals with your physical connections. We'll move on to layer two. Layer two is where you're going to get switches. So instead of a hub, this will now be a switch. And I should also mention within a hub, anything connected to a hub, they're all in a single collision domain. What's nice about switches is each individual port is its own collision domain. So carrier sense multiple axis probably more likely isn't used with switches because of the fact that each port is its own collision domain, so there's really not a chance of getting a collision. So with a switch, how a switch functions is, let me look at my notes here, even though I know how a switch functions, but I have no brain for it. Prevents collisions by buffering data. And when it buffers data, it means if the PC is sending a packet to another destination and it's a large packet, instead of trying to send it all at one time and causing congestion, the switch will buffer. It will hold within its memory pieces of that frame, and then it will send it out as it can. So that's what it does for buffering. We should also probably talk about how PCs and how these devices communicate. PCs, routers, printers, they all transmit on pins 1 and 2. So if you have an RJ, we'll say this is an RJ45 connection here. You have 8 pins. Typically there's 8 wires or 4 twisted pairs in a UTP cabling. So PC, router, they transmit on pins 1 and 2, and they receive on 3 and 6. So that's what make this T's transmit and receive 2, 3, 4, 5, 6, 7, 8, and 6. And then switches and hubs transmit on, let's say this is our switch here. 2, 3, 4, 5, 6, 7, 8. This is our PC or our router. This phone router. And this is our switch. They transmit on pins, they receive on 1 and 2 and transmit on 3 and 6. So if you think about that, you have a router and a router, well, they both transmit and receive on the same pin. So to make that connection, you have to use a crossover cable, which crosses the pairs so they can still communicate. The way I like to remember it is, any like device, go ahead and use a crossover cable. If it's this light, it's going to take a straight through cable. If that makes sense. And probably talk about MAC addressing, what a MAC address is. MAC addresses are used by the NIC cards in the PCs and routers and equipment. It's a way of identifying who you are on the network. The MAC address is 6 bytes. So 6 bytes, they divide it in half. So it's 24 bits. We'll just do a simple, we'll say this is a MAC address. They pretty much divide it in half. The first half is the OUI, is the organizational unique identifier. That's each manufacturer has to put a certain code that the IEEE tells them that they have to put in there for this first half. The second half is your NIC. That could be unique to each individual NIC card or whatever the card is within the equipment. And that's really how they identify who's who on the network. So there's different types of ways that the computers communicate. One would be a unicast address. In our example here, we pretty much use a unicast, which means a single device is sending a packet or a frame to another device. A broadcast packet would be everybody on the network would receive that packet. So if PC2 sent out a broadcast, PC1 and PC3 would receive that. A unicast, or not unicast, broadcast, multicast is a packet that a PC would send out and only a select few should get it. So the way I try to remember that is a unicast is 1-to-1, a broadcast is 1-to-all, and a multicast is 1-to-many. That's helped me remember the difference. And we can get into framing. Framing's pretty cool. It's kind of complicated. It's still pretty cool. So when the computers wanted to talk, there had to be some way for them, a standard for them to communicate, so that way any device could communicate on the network. So a layer 2 function is framing. And this is basically just what a frame would look like, a unicast frame for Ethernet. It starts with a preamble. Cisco likes to say it's 7 bytes. And after that you have a starter frame delimiter. And you have your destination and source MAC address. So when PC2 was sending something to PC1, its destination MAC address was this guy's MAC address and the source was his. And then when the PC1 sends the data packet back, it switches the source and destination so they can communicate. The length and type field was interesting to me because the type would describe the type of packet that's in the next part, which is the data in the pad, whether it's TCP, UDP, or an IP packet. And then at the end, the FCS is frame checking sequence. Layer 2 provides your error detection, but not error recovery. So at layer 2, if there was a problem in transmission, the frame check sequence would allow the computer to check and see if something happened, if there was some kind of attenuation or a loss of a packet in between. So it's error detection, but not recovery. Recovery happens at layer 4, but you'll talk about that all later. That's pretty much it. That's Ethernet in a nutshell. I hope you enjoyed it, and thank you.